Morning, everyone. It's great to see such an assembly of wizened faces. Yeah. It's a pretty big space, so speakers are going to have to speak up, use the mics. But I just wanted to welcome you all to our workshop, Polar Perspectives. And what we were trying to get at when we conceived this plan was basically a pretty blatant first attempt at trying to put together a community perspective on the merits of a polar mission. I'll rip off some of Don's language and say that this is not pie in the sky anymore. I think technologically it's very feasible. We're going to hear from Les Johnson in the next couple of days, and maybe repeatedly over the course of the workshop, that this is possible. There are now small sat platforms that can get there. They can either, and hopefully with the development of solar sail technology, maybe you can also hold in position over the poles. And not in 30 or 40 years, but maybe in the short time frame of only a couple of years. And so I won't take very long. I just want to welcome you all. We'll have a short presentation from Cheryl, who's been doing a lot of the work in the background about logistics. But this, please avail yourself of all of the facilities around here. The cafeteria is over to the right-hand side, and most of us will be having our lunches there. It should be a beautiful 67 degrees outside today, so not baking hot 100 degrees like it was last week. So it'll be nice to go outside and perambulate should you wish. So when I was thinking about this, and this is kind of like my last slide, thinking about, questions that you're going to hopefully hear discussed over the course of the next couple of days. What are we going to learn about helioseismology from a polar perspective? I mean, the idea here is we've got pretty beefy talks, but we've also got plenty of time for discussion. Because ultimately, at the end of the workshop, we want to try and come up with a list of objectives, a list of polls, targets to aim at. What are the science objectives we could accomplish with a polar mission? What do we think, in the words of Thomas Zabukin, who I spoke to a couple of weeks ago, he's like, what concepts, what ideas can you shatter within a few days of taking observations from that kind of perspective? So have a think about that when you're framing your discussion and when you're posing questions. What can we learn about coronal heating and solar wind acceleration that we don't know from our present plane? The list here is pretty extensive. How could polar observations improve our ability to forecast space weather? All of that stuff's going to be relevant, and I'm sure we're going to hear many, many perspectives and ideas that are a bit more half-baked or actually more complete. And so I'm not going to take up any more time. I want to sit and listen and participate. So I'm going to hand over to this morning's chair, to Michael Thompson. Oh, after, of course, Cheryl. So here's the boss lady coming up to give a talk. If anybody needs anything from Cheryl, I'm sure she'll be more than happy to oblige.
I'm not going to bother to switch this out. Welcome, everybody. I trust that your travels here were pleasant. So just a couple of housekeeping things. You're welcome to either upload your presentations to our Mac computer. You can do that online up to the Google Drive. There's instructions on the website. Or you can bring your own laptop or a thumb drive. Restrooms are in the back, out the door and to the left. Tomorrow we will provide lunch. Let's see, the agenda online and outside the doors here are accurate. We've had some last minute changes, so the printed ones have a couple of changes. So anyway, online and outside the door. If you would like to share your presentation after the conference by sending me a PDF, or if it's okay if I make one out of yours on the machine, we will link that back to the agenda so everyone can have access. We're also recording and webcasting, so those links will also be provided on the agenda online. If you need anything at all, please feel free to email me or find me. I can help you out. And sorry again for the shuttle mishap this morning. We have straightened that out, so going forward, you should be able to get back and forth from the hotel without problem. So welcome, and thank you very much.
Thank you, Cheryl, and good morning, everyone. So we're going to move straight into the first talk of the morning, which is by Sarah Gibson, Solar Physics from Unconventional Viewpoints. Sarah and other speakers would like to leave, I think, 5 minutes probably for discussion questions at the end of the talk. So I'll give you 5 minutes warning before that 5 minutes.
Yeah, I'll just have to get back in. Okay. And I'll probably be a little bit short because I'm just, well, let me get started and I'll tell you what I'm going to do. The title and the abstract here, actually belong to the poster that I've put up over here. I originally put it in as a poster abstract. And it's a poster which is basically looking at what kind of science you could do by getting out of the Sun-Earth line. And we actually consider the polar perspective, but we also think about the perspective from quadrature and the far side. And we talk about the open science questions and what existing and planned missions give us, where the gaps are, and how they could be filled. And so I encourage you to look at that, and it's something which might be useful in our discussion, especially on Thursday. I should show you, there it is in its small form. But what I thought I would do today is something a little bit different, because this is just a sort of a kickoff talk. And I figured I would also get a jump on a talk which I have to prepare for the STO meeting in November. So I'm going to switch the title and switch the content around. I'll touch on some of the themes and some of the questions raised there. But instead, I'd like to talk about flatland. And some of you may be familiar with this story. It's quite an interesting story. It's a story about a square, about a world where everything is two-dimensional. And there's a square who has a sequence of dreams. In the first one, he goes to Lineland, to the one-dimensional world, and he tries to explain to them about the second dimension without much success. He then is later visited by a sphere who in turn explains him and in fact enlightens him about the third dimension by letting him fly through space and see her circular cross-section change as he goes up and down. And he then goes back and tries to share his knowledge of the third dimension to the rest of the people or the characters in Flatland without, again, much success, and ends up in jail, et cetera, et cetera. So, you know, the analogy, I think, is pretty obvious to the polar perspective, so I've changed things a little bit, and so it's beyond Flatland, and instead of a romance, it is a star of many dimension by a square, and I've taken the authorship here, and again, here I digress a little bit from the original Flatland. Flatland was very much a satire of Victorian norms, including gender and social classes. So for example, the men were all polygons, where the workers were triangles, and with each additional vertex, you got a higher and higher class so that the ultimate would be a circle. The women, on the other hand, were line segments, and the men lived in fear that they would meet a woman head on and mistake her for a point and get skewered, which I thought was pretty amusing. But anyway, I digress. Let's go back to the sun. So if there's one thing we've learned about the sun in the many years, centuries millennia that we've observed it, is that as we advance in our technology and in the way we observe it, we learn more about its complexity. So, for example, from the simple sun in the sky with its rays as we draw in a child's portrait, when we could observe with a telescope, we were able to really confirm the presence of sunspots and to see that it is not a perfect sphere. As we go to multi-wavelength observations, here's a picture of Skylab, we can see the structured atmosphere that is visible, for example, at short wavelengths in particular. As we go to higher and higher resolution, this is a picture of AIA, we see the dynamics that's revealed and constantly is amazing us. With helioseismology, we could get below the surface and penetrate its depths and see the patterns of rotation and shear. And most recently, perhaps, with stereo, we got our first 3D perspective from the twin spacecraft of stereo. So what are we going to see if we go to a polar vantage, if we can fly above, if we get a continuous view of the poles? Well, in this poster over here, we broke it down into 4 science areas. The solar interior and dynamo, and we started out by asking what are the remaining open questions in general. And in the solar interior and dynamo, there are questions about the flows and the magnetic field patterns, how they change with longitude, with latitude, with depth, and how they constrain dynamo models. For the solar atmosphere and global connections, we have many questions about the structure of the global coronal and heliospheric magnetic field. We want to know about the source regions of the solar wind, how magnetic energy is stored and released during an eruption, and what is the role of magnetic helicity, magnetic topology. And then as we move out to the solar wind and the heliosphere, the question of how do transients evolve and interact with the ambient solar wind as they move through the heliosphere is still very much an open question. And finally, space weather has its own unique needs for prediction and modeling. And how can we improve our prediction of space weather on timescales of days, weeks, months, or longer? How can we improve the forecast of space weather impacts at the Earth and throughout the solar system? These are all general open questions, and we have a lot of good observations now that give us information. We have models, we have new telescopes, we have Parker Solar Probe coming online, we have Solar Orbiter coming. And so the question is, and this is what this gap analysis in the poster attempts to do, what can we specifically learn from a polar perspective? And so let me take them one at a time. And these are not a complete set of questions or a complete set of new capabilities that will shed new light on these questions, but they're a set that maybe can start some conversations, and I'm sure we'll have more talks as we go on, leading us to other ones. For the solar interior, helioseismology, local helioseismology in particular, depends on having ray paths. And so if we have more than one view, we potentially could have longer ray paths. If we could observe flux emergence at all longitudes, for example, from the polar view, then we could see the evolution of active regions and the evolution and the formation of polar crown filaments, coronal holes, etc. If we could observe the North Pole independently from the South Pole, there are various symmetries that we could break. And perhaps most importantly, we could directly observe the polar magnetic field and the flows at the poles. For the solar atmosphere and global connections, what could we do? Well, one of the most fundamental things is having that boundary condition much better represented by observing at the poles. The global magnetic boundary is very much held back by our limited and foreshortened observations at the poles. The magnetic vector boundary with more than one view can be disambiguated. 3D coronal models of stereoscopy or tomography, if we have multiple views, are obviously helped by having the view from the pole. And the simultaneous limb disk view of CMEs and their precursors, as we look down from the poles at a structure at the limb, which we then can see from the Earth on the disk. Would help us really get at, this is something we get from stereo, but getting that same view from the pole, or rather that different view from the pole, likewise gives us fundamental information about the structure of CMEs. And finally, the global interactions, when we have, for example, sympathetic eruptions, when we have an eruption which is related to an eruption elsewhere at a different longitude, the poles give us a really unique angle on that, because we can see, without this foreshortening, the structures interacting with each other. The solar wind and the heliosphere. Here we get, and I'll show you a picture in a moment, a very nice view, which is the view looking down, the fried egg view of the heliosphere. And we can see how solar wind source regions connect to heliospheric imaging and in situ measurements. We can see the longitudinal structure of, for example, the Alphane zone. I should really put quotes around the entire thing. Lately, there's been observations that imply that the concept of an Alphane surface may not be accurate, that it may be much more fractal in nature. To observe that in the basically the ecliptic plane would be a unique capability. and to be able to see CMEs and CIRs and shocks in that view. And then finally, getting more lines of sight, again, to reconstruct the 3D solar wind structures. And finally, space weather. Again, the longitudinal coverage allows us to see the seasons of space weather. Active longitudes form and persist. It allows us to monitor and model Earth and planet intersecting transients. From the pole, every ecliptic CME is going to be a limb CME. We won't be seeing halo CMEs. This would improve our boundary condition on space weather models, improve arrival time predictions, improve predictions of trajectories, we have the potential, and I have an example of this in the poster, of measuring actual BZ, southward magnetic fields, as they leave the sun. The magnetic field, the north-south line, is the line of sight when viewed from the pole. So observations, for example, in circular polarization, in coronal polarimetry, or for that matter, observations of Faraday rotation, which are sensitive to line of sight fields, would have the capability of directly measuring the BZ field as it leaves the sun. And then again, the evolution in the solar wind. This is that fried egg, in fact, indeed, sunny side up view of the heliosphere. And on the right, what you're seeing is a heliospheric model where you can see the Parker spiral, but you can also see a CME coming out. Through the heliosphere, you can see the co-rotating interaction regions with a truly unique perspective. And finally, as Scott said, what are we going to discover? We keep showing these pictures of Jupiter or Saturn and what was found at their poles. And yes, we had some ideas from theory and models that we might see some very curious and marvelous vortices, but did we ever expect a hexagon? What will we see at the sun? On the upper left and right, on the upper left we have a picture, measurements of local departures of near-surface velocities. This is a paper by Bogart et al., seen from a polar perspective, using very high latitude views, and you see that spiral pattern. On the right, you have a coronal hole pattern observed using the Macintosh archive, again using low latitude, low resolution observations of coronal holes and polar crown filaments. And when we look at that archive, and we look through nearly 40 years of observations from this polar perspective, you see these spiral structures form and spin up and spin down. How will they appear when we see them directly from the pole itself? What will we learn about irradiance? What will we learn about stellar irradiance by observing our star looking down from the poles? There are things we don't know yet. There is real discovery space here. And so I'm going to leave it at that, and I'm looking forward to all of the talks and all of the discussion over the next few days, because I think we're embarking on a really exciting era in solar and heliospheric physics. Thanks.
Thank you, Sarah. And we have plenty of time for discussion, questions, comments. I think that was a really, really nice start to the workshop. A somewhat comprehensive view of the space of opportunities. So we have time for questions, comments. I'm going to ask one. Oh, sorry. Yeah, Dean.
I think it really depends on the science question you're asking. Some of them you're going to need more, some you're going to need less, some you're going to need a longer continuous time period above the poles. And in fact, I think that's very much something I think would be a wonderful achievement of this meeting, is to try to pin down some of the science requirements to achieve these goals.
So Scott mentioned Thomas Sabukin's question of what is it we're going to learn that's going to overturn things in, what was it, 3 days? You have any thoughts on that?
What will we learn in 3 days? Well, the discovery space, the things that just smack us over the head that we didn't expect, we're going to definitely come to. We're going to get some observations that'll be true constraints on existing models of flux transport, the heliosphere, the question of how much open flux there is in the heliosphere and the discrepancies we see. So there are some things I think we'll get reasonably quickly.
The seismology will take a little bit longer.
Yeah.
4 days?
We'll try, Scott, we'll try. Okay, well, thanks, Sarah, again. And so now formally we go into the first session. And our first speaker is Leif Svalgaard. So the session is probing the solar interior from a polar perspective. And Leif is going to talk to us about the mysterious polar magnetic fields and their use for solar sunspot cycle predictions. Again, Leif, I would like to leave about 5 minutes at the end for questions, so I'll give you a 5-minute warning prior to that.
Sort of set up.
I should point out I've got the highest paid techie in the organisation helping us today.
Do you know how to start the section?
Now what? you messed with it.
Full screen mode?
You don't always get what you pay for.
Okay.
Right, so if you can use this mic.
Yeah. Okay, good morning. After these, this introduction, we'll go on with the real meat. And my interest has for a long time been the polar fields. And that's one of the things we want to observe above the pole. But we can see, ever since it was discovered that the sun was magnetic, people have been trying to measure the so-called general magnetic field of the sun. And they go all the way back here to the 1910s. Very first measurements. Oh, I can point with something. This one maybe. Whatever. Aha. That one. Or yours? Okay. So the very first measurements were made by Van Manen at Mount Wilson, and he indicated there was a rather large field, which at the time was sort of, yeah, okay, so what? That's what we expect. But it turns out that those measurements were probably spurious. Jan Stenflo have looked at the original plates, and his revised value is right there, showing no field at all. Then what is plotted here is the actual dipole, the difference between the north and the south. And it sort of goes up and down. And there are obvious reversals, like here and there. Maybe these, but you know, this may not just be errors. But until about the 1950s, where the Babcocks finally developed the Wilson magnetograph, these things were not really believed. They were sort of, yeah, well, you know, the errors were too large. Some people, like academician 70, even believed that there were no changes to the general field. This is one of his magnetograms from 1965, and there's nothing there at the poles above his noise level. And so here, when this was made, we really didn't know if there would be another reversal. So this is has been another. Okay, let me do here. So again, Babcock's wonderful magnetograms. Here, just before the minimum in 53, strong, good polar fields. Then they reversed, and you may not be able to see it, but the slant of these shows the sign. So this is negative. Here they were positive, and here they were negative, but weaker. But he also noticed another thing, which was on the borderline of the noise. Namely, if he plotted a little tick mark, if the North Polar flux looked to be greater than the South Polar flux. You got a little mark here, and vice versa for the South. And so he noticed a variation, maybe, that was in phase with the B0 angle, the tilt of the sun's axis. And his explanation was that, that's the viewing angle. If the polar fields were not uniform, but were concentrated near the very pole, you would see this kind of effect. But of course, at that time, people discounted it. I don't think anybody that were trying to model this or whatever put much emphasis on those observations. But then, I'm so proud to say that we started 42 years ago to measure the polar fields, and our aperture is 3 arcminutes square, like the black one there. And here is what it looks like. We'll not go through this. But we noticed that the polar fields change in a very nice cycle, just as a continuation of the Babcock's or the previous plot shows. We have had our own set of problems. We have scattered light in the beginning, so those fields are too low, should be higher. Here our KDP was this little thing here, failed. So we only measured half of what we did, what we should, but we fixed that by doubling all our data. So, yeah. Then we have a filter that filters out only the green light that we need for centered on 5250. And that got weaker and weaker and weaker and weaker until some point that the intensity was down by a factor of 10 and we were running out of photons. So people finally discovered that and fixed it by putting in a new filter, and you can see things improved. Also, and then last but not least, because that has some implications for prediction of solar cycle 25, we noticed that the electrolincy at the bottom of the pit was dirty. Half of it was covered with junk. We are still debating whether or not that was Coca-Cola or coffee or something. But ordinarily, you're not supposed to spill things down. But so, and that lasted for the first half of 2017. Cut the field basically in half because we only really got from that part. That we have fixed now by a simple procedure of just washing the lens. So. And then we have gone back and fixed all the bad data. Anyway, so, but the bottom line is still that we think we have a pretty good idea of what the polar fields were. You can see, of course, here the annual variation that Babcock discovered. And what we plotted here is we plot the southern hemisphere in red with reversed sign. So you can see here, for example, when the North Pole is weak because it's behind the limb, the South Pole is strong, and so on. That's not a problem. And so this is just, we analyzed our first 2 years of data, and we found that this yearly, the amplitude of this yearly variation could be explained by a top knot concentration near the pole, something like that. And various people have done that since, and they find in this number here to be in the range from 7 to 10. So there is a concentration near the pole, and already here back in 75, Bob Howard, stacked magnetograms, and you could see the concentration of polar patches. Jan Stenflo back in 68 even found that. And then, last but not least, he noted data sees those strong kilogauss concentrations, which are unipolar, so the polar fields even at that resolution, seem to be unipolar. What we don't know, of course, is what's hiding in here. So we need good high-resolution data from over the pole. So how does the flux get there? How come we have this concentration? And it's now generally believed that the meridional circulation carries low-latitude flux to the pole. And here's what is called a super-synoptic chart, where you simply compress the synoptic map to a thin slice, and then just put all those slices next to one another, reversing the time in each, because synoptic charts time goes the other way. So here you can see how the negative and the positive flux move, both of them, to the pole at the same time. Often people show plots like that, where they take a rotation average, but that washes out this thing, so you get a rather misleading image of what is going on. But of course, this is not news. People noticed that a long time ago. And so, what do we see today with our beautiful HMI? So here's the last year or so, and we are right now here or there. You can see that the negative and the positive flux move together, and probably cancel between them as they move. And only a very small fraction of all that flux ends up in the poles. And just to show here that the polar holes that we see are not, as people believe, extensions of the polar cap that spiral down and so on. No, they're just flux moving towards the pole. Here is somebody plotting the polarity of coronal holes over time. You can see for yourself. All right, so the Babcock observations showed that what happened here is something happened in the interior of the sun, winding up. He even predicted from his model that there would be a tilt between the two polarities. And then, of course, we have a theory about how the sun sheds this magnetic field. But Bob Layton, way back then, even showed in this one here that the polar fields given by those follow about 5 years after the maximum sunspot number. So here we plot the tilt basically between the two polarities, and you can see that changes with the cycle and has a 17-year period. And cycle 25 is down here, so it has already begun. And there's a very strange effect of that tilt, namely that the west side of the sun and the east side of the sun are different. So this is superposed all HMI magnetograms up to the end of that year. And you can see it's more blue here and more red over here. So that's simply because of the tilt of the two polarities. So we're talking about now the extended cycle, and that's what it looked like in 1991. Can we even agree that there is a cycle? Can I have a show of hand? Who believes there is an extended cycle? 1, 2, less than half. Okay, so that's the state of the art. But here comes now Mr. Scott and company, and counting bright points. And those bright points also show a 17 or 18-year cycle, an extended cycle. And so and even in the torsional oscillation that we measure below the surface, show this 17, 18-year cycle. So that's something that happens in the interior, and we don't really know what that is. We cannot even agree that there is such an effect. And so, very short about them. Meridian circulation, the various people find various things. One cell, two cells, complicated structure that changes from year to year. So how can we explain the extended cycle? That's one of the problems we might be able to solve. And we can actually get a feeling for what the polar fields are back in time. So we believe we can carry that back to the 1840s. And so here are the polar fields. And we can even make a prediction based on that. Our prediction of solar cycle 25 is here. Makes it somewhere between 24 and 20. The polar cap flux is also, as Kernel points out, the driver of the heliospheric field. And so here we have observed reversals. The question is, does the sun polar fields reverse way back here in the quantum minimum, for example? And that's another question we don't know. But we can derive that interplanetary field from the geomagnetic indices. This is a magnetosphere of the Earth, and where is B is the magnetic field, and V is the solar wind speed. We can construct indices that have different dependencies on B and V, and from that we can actually determine both. So here is a reconstruction of B at Earth back to 1840 or so. There are two of them. There's our own with the red and the competing group by these people, and we finally got to the point where we now actually agree. 10 years ago it was not the case, but eventually somebody has seen the light. We can measure polar fields in a different way, where we don't have the problem of foreshortening. Quite the contrary. This is good, namely the microwave images at 17 gigahertz. This is the array in Nobayama in Japan, and that's what they measured. Here are the south polar fields, and that's the ether coronal hole as well. And there, of course, we are looking through a whole bunch of structures. So we collect the signal, we get a good signal. Once we are in the middle of the disk, the chromosphere is thin, so we don't see any emission in that. So that's another way of actually getting, let's say, polar fields without having the foreshortening problem. And we can do that plotting as a function of position angle simply going around the sun, and we can see how the polar fields grow and decrease, grow and decrease. And these are the sunspot zones. So it's another way of doing that. We can be a little bit more specific. We can plot the excess brightness temperature measured in that wavelength, and it's here. And there's the polar fields measured at Wilcox, and you can see how well that they match. And we can skip that one. So I will end by a quote from Magnus Clark. With very nice 19th century prose there, right? So the question here is, have we made progress? Maybe we have, but not much. And Jack Eddy had this to say: we need imagination, but not too much of it. Right? And no matter what we do, we have this problem, right? So, so that's the end, okay?
Thank you, Leif.
Okay.
We have time for comments, questions, discussion.
Tom?
Tom?
Yeah.
Can you elaborate a little bit on your statement that coronal holes are really extensions forward and not vice versa?
Well, I showed a slide of that. If you find all the coronal holes and mark their center with blue or red, and then follow them, you can see how they move up. Okay? So you can also see that directly from the magnetograms, okay, where the super synoptic chart shows that very clearly. So this is a thing that's been misinterpreted for decades now. The coronal holes are not extensions of the polar cap. They're just quite the opposite. They're flux moving up into the polar cap. Okay? And so we don't need to explain why the spirals move out. We have to explain how the spirals move in. Okay? So, anything else?
Scott?
Is there a time frame that would be preferential? You know, if you were to go and say, like you showed a lot of things, you talked about the extended solar cycle. Is there a time where you would want to especially be observing the poles relative to the low latitudes?
Yeah, the answer to that is all the time. Or put it more practically, we will take what we can get, right? But I think a time at maximum is important, the time when they reverse. So one of the sort of unsolved question is, do they reverse because we have equal amount of both polarities, or do they reverse because one polarity disappears and the other one is there? So that's an important time. Of course, a solar minimum is also important. So if we can get the first shot at solar max and then keep the thing alive for another 5 or 6 years, I'll be happy.
I think that's the difference between station keeping and orbit. So if you're going to orbit, you need to synchronize an orbit based on a model projection of when that's going to happen.
Right. That's important. And as to the amount of data, I want to remind you that only a few weeks of data proved the existence of the solar wind. Once we got there it was. It was low-hanging fruit, basically. Same thing with the Van Allen belts. You know, it's and with the rotation of the radiative interior. I mean, it only takes one good observation to show that. The rest is a bonus. Huh? Okay. Any more?
Any other questions, comments? Very neatly preempted my question, the Zabukan question, with your last
Right.
with your last words. So in that case, let's thank Leif again. Our next speaker is Aaron Birch. He's going to talk to us about helioseismology from a polar perspective. We'll try and leave 5 at the end for questions. I'll give you a 5-minute warning before that. Here comes the techie.
Hello? Is it coming? Okay, great. Thanks, Mike. So yeah, I'm going to talk about helioseismology from a polar perspective. Here's my list of topics where I think helioseismology could make a difference. There's a question of what are the large-scale flows doing at high latitude? So the meridional flow, the differential rotation, and the torsional oscillations. There's the question of the convection at high latitude, and here I'm thinking about convection at the scale of supergranulation. And a few things that would come along with a polar perspective but aren't sitting at the pole. Or you could look at sunspot oscillations with stereoscopic observations. And also, I think there are interesting questions about mode physics, so the physics of P modes, that could be addressed with stereoscopic observations. Just to make sure that we're on the same page about terminology, I wanted to go very briefly over ways of measuring flows. Helioseismology, there are two general classes of helioseismology. One is global mode helioseismology. This is based on measuring resonance frequencies. And from these frequencies, you can infer axisymmetric and north-south averages of flows and structure. So things like differential rotation. With local helioseismology, you measure wave travel times or local dispersion relations. And from these, you can infer three-dimensional structure and flows. And then I'll throw these into the same bucket as well. Local correlation tracking is about tracking the motion of features on the surface. And which features you track depends on what it is that you're trying to do. So for example, you can track the motion of granules, you can track the motion of small magnetic features. And something that I think should absolutely not be overlooked in the context of a polar mission is the tracking of supergranules. People don't use this very often, but it is a perfectly reasonable way to measure larger scale flows. You want to measure flows that are larger than supergranules. And it has the advantage of it's just very, very light in terms of telemetry compared to, say, what you would need to do to track granules. And then there are direct Doppler observations as well. Well, why a polar perspective? I guess the first one, it's painfully obvious, but it has to be said. We can see the poles. That would be great. You can go and do local helioseismology and measure flows, or you do correlation tracking and you measure flows in the polar regions. But there are a lot of things that you get in addition to just the simple effect. And these things come when you start combining observations from the polar mission with observations from other instruments. So for example, from GONG or HMI or maybe even Solar Orbiter, depending on the timing. And you can do a lot. An advantage is that you can follow features for longer and or see more of them. So something that would fall into this class would be active regions. You would see more active region emergences and you could follow active regions for longer. There's stereoscopic helioseismology. So here I'm thinking about local helioseismology where you use one instrument to observe one end of a ray path and another instrument to observe the other end of the ray path. And this was mentioned earlier. This gives you access to ray paths that we just can't study right now. So this is exploration. And then the final category here is stereoscopic observations of a particular feature on the sun. So you're using two instruments to study the same patch of sun. And this gives you two components of velocity and two components of magnetic field. And I'll talk a little bit more about that later. Okay, large-scale flows. The first example I wanted to talk about is the meridional circulation. This is a time-dependent flow. Unfortunately, right now, it's also a method-dependent flow. I trust that will be solved. One of the big issues is that there's unmodeled physics in the P modes. And this causes a large-scale and very strong center-to-limb effect. I won't say more about meridional flow. Rudy and Junwei are going to take care of that topic later. Another example is the differential rotation and the torsional oscillations. We've seen this figure already. This is showing torsional oscillations as a function of time and latitude. So the question is, well, what's going on off the top of this figure? Another topic is what's happening with the supergranulation at high latitude. This is a figure from a paper by Kaori Nagashima. This was helioseismology of near one of the poles done with Hinode observations. Because the resolution of those observations is so high, you can go to quite high latitudes. There's still a hole in the middle, and there's also the question of what is the time evolution of this pattern. I mentioned earlier sunspot oscillations. This is what I was thinking about. Imagine you have your sunspot. You have two instruments with different lines of sight. Now you get two components of velocity and you get two components of magnetic field. And this would help with distinguishing the different wave modes that are happening in a sunspot. And ultimately, it would help with sunspot seismology and the interpretation of local helioseismic measurements of wave propagation in sunspots. Yeah.
Either go closer to there or use the mic right there. There's one on the left. There.
Okay. Yeah, no, I can stand closer here. Is that better? So another advantage of having two instruments is, and one of them out of the ecliptic, is you get better coverage. This is an example of what you can do with one instrument, so one instrument sitting in the ecliptic. These are calculations of kernel functions for helioseismic holography. They're done by Dan Yang. He's a student at the MPS. He will be defending in December and on the job market. He does great stuff. Here's an example. So this is the kernel calculation. This kind of orange color is saying what your measurement is sensitive to. So this is, you're doing holography, you're trying to measure the theta component of the velocity, so the north-south component of the velocity near this target location. And this kernel function is all spread out. It says you don't have a lot of spatial resolution. If you add a second instrument way out of the ecliptic, this is what you get. Now your kernel function is much better localized. And it turns out also that the signal-to-noise ratio for a little flow here goes up by about a factor of 3. And I'm not showing this really to get into the details of the calculation or the numbers, but the point is that these kinds of facilities are coming online. We're starting to be able to do these kinds of calculations and predict, what we would expect to see in different scenarios. I wanted to say a little bit more about mode physics. I think this paper by Baldner and Sko convincingly showed that the P modes are interacting significantly with the near surface convection. And a consequence of this interaction is that the phase of the P mode eigenfunctions depends on height in the atmosphere. And a consequence of that is you get a large-scale center-to-limb effect. Because as you look further from disk center, you're looking at a different height in the atmosphere, so you're seeing the oscillations with a different phase. And if you could make observations, stereoscopic observations, you would be able to directly measure the phase of the eigenfunctions as a function of height in the atmosphere. And at the very least, this would provide constraints for models. But I think there's some hope of developing an empirical correction based on these kinds of measurements. I wanted to say a little bit about requirements. So for any of these science topics that I've been talking about, we can go in and try to determine the requirements on the observations. So for example, the resolution or the cadence. And we've been through this exercise not too long ago, thinking about observations from Phi on Solar Orbiter. And there's a nice paper by Bjorn Liptjen about this. It has this figure. I'm now going to go through this in excruciating detail and explain every line to you. No, don't worry. But the point is that you can think about any of these science topics, and a lot of the things I've talked about today are on this table. So things like what kind of observing time do you need to measure the meridional circulation to 3 meters per second at 75 degrees? And you find this box. It says 100 days. Red here are things that were not going to work in our understanding of the constraints on Solar Orbiter at that time. And you can compute how much telemetry you need. So you see numbers like 100 days here for the meridional flow. You can go down to something like a few days for measuring sunspot oscillations. And I wanted to say just a little bit about why does helioseismology often need such long time series? And the basic answer is signal to noise. The noise goes down slowly with the observing time. It goes like 1 over root t. This is the case for noise due to realization noise, so the stochastic excitation of the oscillations, or noise due to supergranules. And at the same time, you need a relatively high cadence because you have to capture the P modes. And that can be a tough combination. Long duration observations at high cadence. And so you can worry about telemetry. One thing that can help is data compression. This is a calculation again from Liptjen. And it shows signal to noise ratio. This is for some time distance measurement of supergranulation. So y-axis is signal to noise ratio. X-axis is the compressed file size. And he played with a lot of different ways of compressing the Dopplergrams. And I don't want to go into all of that. But the important point is that the middle of the x-axis, you're sitting here at 1 bit per pixel. That's pretty nice. And you can find compression methods that are not hurting you at all in terms of signal to noise. Of course, we have to think about this in the context of what other things people would want to do to the data. We don't want to mess up someone else's observations. But for the helioseismology, I think compression is something that should be thought about. All I wanted to say here is that example was for measurements of supergranules, which are just about the easiest thing to measure in local helioseismology. But we could go through this kind of exercise for other targets as well. So by way of summary, I think there are important science questions: large-scale flows at high latitude, supergranulation at high latitude, sunspot oscillations, P-mode physics. We understand relatively well how to compute requirements at this point, and we've been through the exercise for Phi. And I wanted to end on something that I didn't emphasize in this talk, but it needs to be said, and it needs to be said again, that there's also an exploration aspect to this, that when you have stereoscopic observations, this will give us access to new ray paths. And who knows, maybe there are some very big surprises once we start making those measurements. Yeah, that's what I wanted to say today. Thank you.
Thank you, Aaron. Time for questions. Don?
Yeah, Aaron,
And Thierry.
the option slide, the table.
The table.
Yeah. So that was done for Solar Orbiter at 30 degrees latitude, right?
Yep,
So if you had a vantage point higher than that,
yep.
can you more direct view, can you bring that 100 days, for example, for the meridional circulation? Can you bring that down?
Not by a lot. That the limit there is basically how many supergranules do you have messing you up, and the number of supergranules depends on latitude. Yeah.
Gary?
Yeah, Aaron, what you showed is mainly the context of solar orbiter.
Yes.
The missions that you're thinking about.
I have no idea because I don't know about the mission we're talking about now. For example, I don't know anything about what would be the requirements or the limits on telemetry.
What would be the requirement for solar orbiter?
More telemetry, please. Yeah, and yeah, this is another issue. Maybe you know the latest, but the last I heard is that the solar orbiter remote sensing instruments would not be allowed to observe outside these 10-day remote sensing windows. I know it's being discussed, but I don't know the current status.
Dean?
So you're doing time distance helioseismology on the spacecraft and then sending map results down, or are you sending low resolution Dopplergrams?
Yeah, these telemetry requirements came from assuming you were sending Dopplergrams at 5 bits per pixel. And yeah, it's something to think about. And we went around in circles on it. You know, should you try to do helioseismology, say compute the cross covariances on board? Should you try to do correlation tracking on board? Yeah, it's a question and a thing to think about.
I had a quick question about, was it Dan Yang's kernels? So was it really, does the wider pupil, the wider coverage of the surface really help here, or is it just that you need to have a pupil that's vertically above the target?
Yeah. If I had to guess, I would say it's mostly that you have a pupil above the target, but I'm not 100% sure.
Okay.
Yeah.
So in the left hand slide, as you move the target, as you rotate it clockwise, the antipodal kind of sensitivity would disappear.
I expect that's the case. Yeah.
Michael, we should do the Zerbuchen question, right?
Oh yeah, go ahead.
No.
We want the Zerbuchen question.
Yeah.
Yeah, this is a hard one for helioseismologists.
Yeah, for 3 days? Was that the cutoff?
Well, what's
few
the early discovery space do you think would actually be kind of potentially paradigm shifting?
So there's hope for measuring convection at high latitudes. Are the supergranules doing something really funny in their evolution at high latitude? We know the Coriolis force matters for supergranules. So maybe there's something interesting at high latitude. Sunspot oscillations, 3 days is no problem. Mm-hmm. Stereoscopic observations to understand P-mode physics in 3 days would potentially be really very, very helpful. It sounds technical, but it matters because this large-scale field effect is really a problem for helioseismology.
In terms of the stereoscopic, is there something specific from the polar vantage point that's more important than, say, an L5 or, an L5 vantage point?
I don't think so. For sunspot oscillations or P-mode physics, no.
Right, well, thanks again, Aaron. Our next speaker is Maria Weber, who is going to tell us about how a polar observing perspective could help constrain dynamo theory and the solar cycle origin. Again, we'll try and leave about 5 questions and discussions, so I'll give you
Sure.
time
Oh.
before then. Oh, we've lost our tech guy. No.
Oh, there it is. Okay, yes, I'm Maria Weber. I'm a National Science Foundation Astronomy and Astrophysics postdoctoral fellow at the University of Chicago and Adler Planetarium. I do simulations of solar and stellar flux emergence, convection, and dynamo action. And I'd like to thank the conference organizers for inviting me to give this review talk, where I'll be discussing some open questions regarding the solar interior and cycle and the insight or conundrums that models provide, all with an eye toward the ways by which polar or multi-vantage point observations could help us constrain dynamo theory. So our solar dynamo perspective is largely driven from one vantage point along the Sun-Earth line, and understanding of the sun's poles remains an elusive ingredient to help us address the many questions surrounding the solar dynamo mechanism and the fluid flows that drive it. So being able to view the sun simultaneously from multiple vantage points will enable us to get a complete map of the surface magnetism and gather more information about the deep interior at all latitudes. And in the era of large-scale surveys of solar magnetism, an understanding of the sun's cyclic dynamo at all latitudes will be useful to the stellar astrophysics community as well. So with those points as motivators for a new observing perspective, let's take a deeper dive into some of the open questions surrounding dynamo theory and the solar interior that new spacecraft observations might help us constrain. Some of these will cover a few of the things that we've already heard about today. But in particular, I'm going to be talking about these questions from a modeling perspective, focusing on mean flows such as differential rotation and meridional circulation, torsional oscillations, convective structures and speeds, shearing layers, the tachocline and the near surface, convective and flux emergence links to the dynamo, and the solar-stellar connection. Now, since solar magnetism is generated and sustained by plasma fluid motions, I'm going to start by talking about the sun's mean flows. Helioseismology continues to be a powerful tool for us in solar physics, as we all well know, and the possibilities of future spacecraft missions will help us get a sense of the high-latitude differential rotation and meridional flow structure with depth, and provide us better insight into our tachocline, the shearing region at the base of the convection zone, and the solar near-surface shear layer across the upper 5% of the star, where the differential rotation decreases drastically. What you might not know or get a sense from with these observations is how intimately linked the differential rotation and meridional circulation are to each other. So meridional circulation plays a role in redistributing angular momentum that establishes differential rotation. In global convection simulations, a multi-celled meridional circulation appears as the sun is spun up. And at least for this simulation that you see here, it's multi-celled at solar rotation. And the transition from single to multi-celled profiles is linked to a change in the convective Reynolds stresses. A solar-like differential rotation, prograde, equator, slow poles, tends to accompany a multi-celled meridional flow. Single-celled meridional circulation extending to higher latitudes tends to spin up the poles, driving something like a polar vortex, creating an anti-solar differential rotation that's slow equator and fast poles. So what regime is the sun in? It may be that the sun is near the transition between the fast and slow rotating regimes. So this is an example of a transitional case with a solar-like differential rotation and a single-celled meridional circulation. So this is an area where observations of polar flows will really help us constrain theories of the solar interior. So torsional oscillations are variations of the differential rotation that are strongly linked to the sun's magnetism. So this top image, you've seen a similar one already, shows solar torsional oscillations with the magnetic activity bands overlaid. Those are determined in part from EUV bright points. And the torsional oscillation behavior changes above 55 degrees with remnants that do extend into the next solar cycle. Now, a few different types of dynamo models have been able to recreate aspects of torsional oscillations. Broadly, in these simulations, they are caused by the presence of magnetic torques and the way that those torques modulated other forces that influence zonal dynamics. For example, the transport of angular momentum by mean flows. And using a mean field dynamo model, it has been shown that a reduction in the cycle amplitude tends to lead to an increase of the differential rotation and thereby a drop in the high latitude torsional oscillation signal, possibly shedding light on the differences in the torsional oscillation pattern between cycles. And observations of torsional oscillations at high latitudes and their relation to flux emergence up there at high latitudes will help us motivate and verify these types of dynamo models. So this slide is going to ask more questions than it will provide simulation insight. We still do not have a complete understanding of the sun's shearing layers, the tachocline at the radiative convection zone interface, and the near-surface shear layer across the upper 5% of our sun. Multi-vantage point and polar observations may help us to better probe these regions. Might we learn how the thickness of the tachocline varies with latitude, place limits on overshooting convection at the base of the convection zone, and constrain the magnetism expected in the tachocline? 3D convective dynamo models indicate that a stably stratified tachocline region actually acts to regulate the cycle period, possibly prolonging it. And it isn't also clear how convection in the sub-photospheric layers drives the shearing flows that we find there, although we think it is in part due to a result of the faster overturning convective motions in this region on smaller spatial scales that do not as strongly feel the effects of rotation. Simulations have a hard time recovering the solar near-surface shear layer at all latitudes. So what might the near-surface shear layer actually be like in the polar layers? And how does it impact global convection, the dynamo at all latitudes, and emerging flux? Now, the sun has a hierarchy of convective structures, due in part to the large density stratification from the interior to the surface. Fast, narrow downflows surround slower, broader upflows. Granules on the surface are a few megameters, supergranules 30 megameters, and giant cells are expected to extend most of the convection zone. Downflow plumes merge and entrain into superplumes that penetrate deeper, where the hierarchy results in cells large enough to sense the rotation and spherical geometry of the deep interior. Giant cells are difficult to detect due to convective noise on smaller scales, but simulations suggest that they must be there in order to transport the required angular momentum in order to spin up the equator. Now, global convection simulations show low-latitude giant cells that are elongated and propagate prograde relative to higher latitude cells, and both global-scale convection simulations and those of shallower convection and tilted rotating spheres show a preference for lower latitude cells to be more north-south aligned, whereas higher latitude cells tend to be more isotropic. And what are the typical velocities of these motions? Both observations, which are the lines here in this first figure, and simulations of granulation and supergranulation, which are the symbols here, indicate that all scales of convective motions are part of a continuous spectrum. But the answer may not be so clear when comparing simulations and observations of convection in the interior. Different helioseismology techniques give results that may vary by 2 orders of magnitude from each other, and also from global convection simulations. But we should take care when making these comparisons between simulations and observations, because in some regimes, Featherstone and Hindman have shown that these global scale convection simulations, if they're not run with a sufficiently high Rayleigh number, they may overestimate the low wave number measurements that are accessible to helioseismology. So future observations may help us to get a better grasp of the true scales and speeds of convection at all latitudes. Now, we know that there's a strong observed relationship between emerging active regions and the reversal of the global field, and this process is captured within the Babcock-Leighton flux transport dynamo. Differential rotation produces a toroidal field from the poloidal field of the previous cycle. Portions of this magnetism rise buoyantly to the surface and emerge as bipolar active regions tilted toward the equator due to rotation. And the decay and diffusion of active regions, largely by turbulent supergranulation, becomes a source for the poloidal magnetic field. Some flux cancels across the equator, and then the residuals carried to the poles by meridional flows, causing a polar field reversal, and some of it's transported downward and toward the equator also by the meridional flow. So this process is highly dependent on three key factors: active regions following Hale's and Joy's law, their diffusion and decay, and the meridional flow. So it's important to understand the meridional flow and also observe flux cancellation processes at the poles to verify these types of models. So in this panel is an extreme example of flux transport models in a solar-like star with slow and fast rotation. These models use a single-celled meridional flow that decreases in speed as the rotation rate is increased, and this is a trend that's found in 3D global convection simulations. And the cycle period in these butterfly diagrams lengthens at faster rotations and slower meridional flows. And this trend might be at odds with the often observed shorter cycle at increased rotation observed for cool stars. But in that case, one might want to take hints from other solar flux transport models and invoke multi-celled meridional flows, turbulent pumping, or enhanced magnetic diffusion to modify the cycle length. So here the meridional flow operates like a conveyor belt. Moving on here to the second panel, in solar cycle 23, it was speculated that the surface meridional flow extended to the poles, while in cycle 22 it turned over at 60 degrees latitude. So these, a set of flux transport models by Masumi Dikpati showed that the transport of magnetic flux via the longer conveyor belt of cycle 23 with a slower return flow in cycle 23 compared to that in cycle 22 might have caused the longer duration of cycle 23. And there's also consequences of flux emergence trends within the Babcock-Leighton flux transport framework. So by incorporating a scatter around the mean tilt angle trend, simulations by Vidya Karak and Mark Misch illustrate that the variability of the solar cycle might be attributed to tilt angle fluctuations alone, resulting in periods of grand minima and grand maxima. Rogue active regions, those of unusually large flux or anti-Hale or anti-Joy orientation, can boost or suppress the cycle or even cause hemispheric asymmetries based on the active region individual contributions to the total dipole moment. So these flux transport models are based on our unique observations of the sun. And so I always wonder if such processes are in operation on all stars, especially those that are highly spotted or those with substantially higher latitudes of flux emergence than what we have on our own sun. And so sometimes, personally myself, I struggle with reconciling flux transport dynamos with 3D convective dynamo simulations. Babcock-Leighton flux transport dynamos were created to overcome challenges posed by helioseismology and the equatorial propagation of sunspots. Within these models, you can vary parameters at reduced computational costs, prescribe a priori the meridional circulation, differential rotation, and properties of active regions to understand how they influence the solar cycle. But 3D convective dynamo simulations are able to self-consistently produce cycles and mean flows. With them, you can examine how such flows are built and sustained in the first place, and they are also now showing hints of magnetic flux emergence that might be star spot progenitors. In the context of fully convective stars within these 3D convective dynamo simulations, a strong dipolar field can be built, which actually can suppress convection and heat transport at the poles. So these types of models are parallel approaches to understand the solar and stellar cycles with some different questions and capabilities in mind, but in the end, they do complement each other. And a solar polar observing mission could help us with the solar-stellar connection as well. Stellar activity can be compared to the sun's by looking at calcium H and K emission, which is a proxy for magnetic activity, which for sun as a star measurements are integrated over the solar disk. Regular magnetic cycles from a few 3D convective dynamo simulations are shown in this figure here as the blue symbols, as compared to observations. Many observations suggest that the length of the stellar activity cycle increases with rotation period. But when taking into account the cycle period and convective luminosity of the star, both simulations and observations, including the solar cycle, indicate that the cycle period may actually be inversely proportional to the rotation rate. So observations of stellar cycles are instrumental in helping us constrain dynamo theory. But if we are observing these stars pole on, or at angles relative to their rotation axis, we might have some different results for our observations. The contribution to the total stellar, the contribution to the total solar irradiance of the polar region and the spot or facular disk coverages that may vary with latitude is not well known, and obtaining those types of observations from a polar solar orbiter could help us make better extrapolations between stellar behavior and the sun as a star. So, an understanding of the sun's poles remains an elusive ingredient in dynamo theory. Models of solar and stellar dynamos and convection provide some insight into the operation of polar or high latitude processes, but they don't always align with available observations. So some observations that could really help us dynamo theorists out would be spacecraft missions with polar imagers, full disk Doppler vector magnetographs of the poles for mapping of the polar magnetism and helioseismology. And we could have multi-vantage point observations to allow for 3D mapping of the stellar surface and to improve signal to noise for helioseismology and time distance analysis for longer ray paths to probe deeper into the star. These will help us address many open questions that constrain the solar cycle and stellar dynamo theory. There are also additional areas for discovery which I have skipped today, and that's the possibility of a small-scale local polar dynamo, which might operate on time scales of a few minutes to a few hours, along with granulation or supergranulation. How might the existence of such a dynamo impact global magnetism? And so, with all of that said, I'm certainly looking forward to future observations that further constrain and will definitely complicate dynamo theory.
Maria? Questions, comments, discussion? Certainly, from a seismological perspective, I think certainly your asks in terms of meridional circulation are certainly within the scope of the kind of mission that we're talking about, and I guess we'll hear more about that from the next two speakers. I'm not sure if this is a question for you or for seismologists in the audience, but the issue of wanting more information about the thickness and so on of the tachocline. I wonder if such a mission can actually, in what way would such a mission give us any information on that? Scott.
Is there any way that we could figure out, can the polar perspectives help us at all with stripping away the shower glass and the impact of the surface regions versus what's going on, or maybe going on underneath it? I mean, you saw on your opening slide, you had different scales, the hierarchy of scales. Clearly, if those scales are all taking place, then the surface is creating a lot of noise that's making it very hard to see underneath. Do you have any feeling about whether the polar convection is simpler or more complex than that at lower levels?
I don't have a really good feeling, no, but at least from the global convection models that we have, we do seem to see that at higher latitudes, the largest scales of convective cells tend to become more isotropic and a little bit smaller, and no longer these like nice elongated banana cell type quintessential thoughts that I have about giant cells. So yeah, there might be, I expect that there's going to be some difference in sort of the largest scale flows that you'll see in the polar region. And there's some hints of that in our convection simulations, but how that relates to what you might find with the magnetism, I don't have a good feeling for that yet. Yeah.
So
What's your answer to the Zabukan question?
Could you...
Well, the strict question was, what are you going to learn in the first 3 days?
Certainly,
Paradise.
yeah, certainly for me, like the beautiful images of the poles of Saturn, the poles of Jupiter, like mind-blowing and so much interesting fluid dynamics that goes into creating that. We get that one nice picture of the sun's poles, and that will immediately tell us something very interesting. Or could be boring, in which case that might also be interesting too. So, and anyway, whatever we see there, I think is even from just one image will set in motion some really exciting things. But of course, we want long time scales. I want information about the convective flow speeds and deep interiors. Yeah.
Promise Thomas the front page of the cover of Nature or Science.
Yeah.
All right, thank you again, Maria. Our next speaker is Rudy Comp. Rudy will be talking to us about subsurface meridional flow at high latitudes. Good segue. Can we get technical assistance, please?
Because if you know where that is.
So this is actually a 15-minute slot, so I'm going to suggest we just leave 3 minutes at the end for discussion. So I'll give you 5 minutes warning before that. 8 minutes and I'll give you 5 minutes. 7 minutes.
You want to do it right up when you're calling.
Okay. My talk. How do I get to my talk? Okay, so I don't know.
Michael, where's this?
Oh yeah. I'm on the machine. It's just. Yeah, okay, no, that's fine. So yeah, I'll talk a little bit about meridional flow, and what it's mainly about is sort of I tried to do a guesstimate of what we might see at high latitude when we can see it. When we can see it. No, blue screen. There.
I was too fast, wasn't I?
Okay. You don't need any figures. I can. So to answer Dean's question, I would like to have a couple of solar cycles, please, of observations of that kind of stuff. So, what? Okay. So So what I can tell you we heard already that the meridional flow is important for the dynamo models, and whenever the slide shows up, I can tell you a bit more about that. Okay. And so what we have now is we have observations, helioseismic observations that cover actually 2 solar cycles, because beginning with MDI and then Ngong and SDO HMI. Damn, Max. And okay, see, just have to curse them, then they work. Okay, so yeah, so that's what I'm talking about. And so we know the question has already been addressed in previous talks. What happens is there really just one cycle, one cell, one meridional flow cell that is in like latitude or depth, or is there multiples in any direction? What I'll talk a little bit about is cells in latitude, because since I'm a follower of the ring diagram analysis, so we are just measuring the outer few percent of the surface. And so the question is sort of for me, when counter cells get observed ever so often, counter cell meaning a quarter word of meridional flow. And so sometimes that gets observed, and sometimes then it's the B angle. And so we try to learn a little bit more about that. And so this is an example, again, from one of these modeling efforts. The reason why these kind of cells, if there are more than one cell in the meridional flow, let's say in latitude, what that impacts, it will, for example, it will speed up the cycle because it turns over at the lower latitude, not at the pole, and that then has then consequences. These are two simulations. The left one is a normal single cell kind of, and this is a second cell at high latitude. And the bottom panels is what you would see at the surface, okay, out of that paper. And so what you see is that the cycle length is sort of like 11 years, and here it's then short or 8 something. And what you also see is that then the polar field does no longer peak at the poles, it peaks at a lower latitude. And also that to delay the polarity change, because then the flow, the equatorward flow pushes against the activity that wants to go to the poles. And so that is sort of the motivation why you want to know this. And so that would be something we will learn when we can observe these things. What we can do right now is an example like this. The time goes in the x-axis, y-axis is latitude. This is a snapshot at a particular depth, in this case 7 megameters, because that's one I like. And so what this is, it's the beginning of 96-ish, 97-ish. You have MDI, and it ends with HMI. HMI can go a little bit higher in latitude. You can see these episodic things at 75 degrees. If the B angle is with you, then you see it, and if not, then you don't. And so, but HMI is good, at least at 67. When I say latitudes, this is always the center of a patch, okay, and these have some extent, so that's what that is. MDI in Gong can go to 52.5, which means plus minus 60, and we all know when you observe the sun, if you go above 60, it gets difficult. And so that is a progress. So what the top panel shows is Merino flow is poleward, like we expect it to be. Positive red means to the north, blue means to the south, and so that's what that is. And if you then, the bottom panel shows you, if you subtract then the mean at each latitude, then you nicely see solar cycle variation, just like with the rotation rate. You see the same kind of pattern where you have these kind of yellow, animation. And you see, so these kind of yellow pattern that moves equatorwards, that's faster than average Merino flow. That means it goes a little bit more poleward. And the blue one is a little bit slower, so you have these kind of, what we all know about, right? These convergent flows near the mean latitude of activity, and that marches sort of through the cycles, just the same kind of pattern. And so what I thought is, well, if I want to show this also as a function of depth, what I could do is I could just show you, take a slice at a given latitude and make then a strip as a function of time and depth. And then I just stack these kind of things over, and then you see something like this. This is the same information like the bottom panel, just for the different depths, and it just looks nice. I think the solar cycle just looks nice. So, and since I averaged over to a hemisphere, I threw away the advantage of local helioseismology and averaged again just in the good old global helioseismology time. And so you see this nice pattern, but what you also see is there a pointer? It doesn't matter. That you can see that if you can also imagine it goes sort of poleward. You have the equatorward branch, but like in the rotation rate, is this? I don't want to press too many buttons in case something else happens. And so, but you also see it goes north, and it would be really nice to see what's up there. And so what I can do, okay, yeah. Which one is it? That one, the green, Okay, so yeah, so you have the equatorward branch, but you also think, yeah, in HMI you can see it, it comes down the next one, and something goes up, and so you think, wouldn't it be nice if you could measure beyond that stretch? So what I did is simple-minded. If we're talking on flows on timescales of a rotation and longer, right? Because I'm doing solar cycle things. So then I can simply assume the Merino flow is probably going to be 0 at the equator, and it's probably going to be 0 at the poles. It's a pretty reasonable assumption since nothing squishes out at the sun, and so far the matter in one hemisphere of the sun has not piled up in the other. I mean, the sun doesn't do that, and the equatorial bulge at the sun has not been that great either. So I think this is a reasonable assumption on long time scales large spatial scales, okay? And if you that's the usual reason why you fit polynomials to the Merino flow. That just goes this way, right? It's just 0 at the poles and the equator, simple. And if you do that, and then you get this one, and of course, since I fitted that to the observations, lo and behold, it looks just like the observations. Big surprise. And so, but the nice thing is you see a little bit more of this extension towards the pole as part of the solar cycle. So like these bands too, they go up. So you have a bit more of an illusion of the polar band of this thing. And if you then, this is the residual, right? And so if you then add the flow, the average that are subtracted out of it, then you get, flows are poleward, but there are certain times of the cycle where at high latitudes you get then out of, almost done. Out of the consequence out of this fit, you get then these kind of equatorward cells that are part of a phase of a solar cycle, of the solar cycle variation of the Merino flow. Okay, and so this blue up here is then a counter cell. So it goes poleward, but not at all times of the, so in the declining phase of the cycle, in this example, you get poleward, Merino flow all the way to the poles, but in the beginning and through to the maximum, you get something that looks countercellish. Again, this is strictly the fit to the observations. The observations go only up to here or up to here in the thing. And this is strictly the sort of, in a sense, it's an interpolation, right? Because I assume that I know what happens at the poles on these time scales. And so what that means is that, the conclusion is basically, like what we all know, the Merino flow varies through the solar cycle. Just like the rotation rate, you see the same kind of patterns, equatorward flow in bands, poleward flow in bands. But you can also, from this, you could sort of imagine that if these kind of second cells appear, they might not be there like in the models, like for the whole cycle, but they would be episodic during certain phases. And the way it just happened magically to appear in my fit is it could sort of be a conjunction with when does the polar fields reverse. So when the Merino flow pushes towards the poles, the activity gets to the poles, the field gets reversed. When the flow goes at the pole is equatorward anyway, nothing goes up there. So you could, so there's potentially a connection between the cells of the Merino flow, or the strength of the Merino flow, or the direction of the Merino flow, and the polar field reversal. And so that's why I said, please, could we have a couple of solar cycles of this stuff? Because then, or at least if not that, but could one have observations that, I don't need continuous 11 years, right? But I would like to have not just a snapshot at one phase of a solar cycle. I would want to have a snapshot at multiple phases of a solar cycle. So otherwise, you see one thing or the other, and then say, done, right? But it might be a variation with a phase that changes direction, even the direction of the flows, not just the amplitudes. And so I think that would be very exciting if we can see something like this. And I'm pretty sure my prediction is the sun will look completely different from what I just showed you, right? So, okay, thank you.
Thank you, Rudy. Comments, questions, live?
Yes. Right, because this is a symmetrical thing, yes. So the hemispheres can do different things, yes. Yes. Uh-huh. Oh, yeah. Uh-huh, neat.
So that's one thing. Can we split it up and get northern and southern?
Right, yes, the reason I didn't want to double up on all the figures, and the neat thing is your noise goes down. So that's the only reason. But I mean, I have done this with of course both hemispheres, and you can see the difference. I mean, the Merino flow, like the original pictures that I showed, like these kind of this kind of stuff. This is, of course, north and south are not identical. So if you look at those kind of flow patterns. So yes, so you can do the same thing. It's just the polynomial fit by definition is the same, but you would then look at so yeah, so it would be very exciting to see what happens, because I expect that the two poles will behave differently, like you found, yes.
Question to either or both of you, do you need those observations simultaneously at the two poles? Do we need two polar sitters?
Yes, the answer is always yes. I mean, always more data.
I thought I knew the answer.
If I can have... Yes.
Ulysses. Questions, comments? Rudy, you said that you didn't necessarily need continuous coverage over a cycle, but so that gives us some sense of what you want in terms of temporal coverage. Could you say a bit more perhaps about the resolution issues that you need? Are you looking for a GONG / MDI / HMI kind of observable from high latitudes, or can you work with lower resolution than that?
Well, you can probably do it. I mean, you always like more, right? I mean, so that's probably the solar orbiter kind of thing. But I mean, the thing with the time scale is, I mean, at the beginning with the MDI, because the dynamics runs were only 2-3 months out of a given calendar year, so you can see that they are. It's nice to have continuous GONG and SDO. I mean, so you can see that, but still, you would see the pattern if you had just like the canonical 100 days that you might need to average out everything else, and then have that every let's say once a year. That would be probably sufficient. But spatial, you can make everything smaller and still survive. But you would have to think about, eventually you get into the signal to noise issue, and can you resolve what you need to measure. So,
there are no more questions, then thank you again, Rudy. Our last speaker before the break is Junwei Zhao, who's going to tell us about polar observations and helioseismic measurements of interior meridional circulation.
I don't know where to find it.
My studies.
Maybe I need to. No. You don't want this.
You want to speak in the mic? Freezing. Yeah, that's what I tried. It's not paying any attention to me. There it goes, there it goes. Joe, last one. This last one. This. Okay. Sorry, this mouse is really obnoxious. Slash. I know. It's there.
All right. So I think it's always bad to be the last speaker for a session, because what I'm going to say was already said by my previous speakers. Yeah, but I will repeat what they said. But I would like to concentrate on the Merino circulation instead of other stuff. So we understand that solar dynamo needs a lot of inputs from helioseismic observations. For example, the solar interior rotation and the Meridian circulation have played important roles in the solar dynamo and the solar phase. However, we also understand that the solar interior rotation and the Merino circulation are not yet fully obtained. This picture has been shown a few times. This is MDI era differential rotation. It has been there for nearly 2 decades, 20 years. So we think it's, the differential rotation is fairly better understood. However, for Merino circulation, it's really, really poorly understood. Only recently we got some results in the interior Merino circulation. This is the most recent picture from our study last year. It covers 7 years of HMI observations. What do we say here is poleward Merino flow in a shallow interior and the poleward Merino flow near the bottom of a convection zone. The equatorward flow is sandwiched in between. This indicates a double cell circulation in each hemisphere. This is a cartoon showing an imagination. However, I would like to point out 2 important points. First, we only see the Merino circulation up to 60 degrees in latitude. So what happens in the last 30 degrees is really important for us to understand the solar dynamo and the solar cycles, but we have nothing for that yet. The second point, and more importantly, I have to point out that this is 3-layer flow structure or double cell circulation is not yet a consensus. After the publication of my paper in 2013, that was 5 years ago, there were 5 papers published so far. Here I collected all these 5 publications, and symmetrized both hemispheres and plot them in the same scheme, same color scheme, same spatial resolution. What's shown here is not that satisfactory. Although I have to point out that all these results are from different instruments, HMI, GONG, MDI, and they cover different time periods also. Despite that, these results are highly unsatisfactory. It gives a lot of differences. If we try to find some consensus, there is a consensus. If we concentrate at just lower than 20 degrees, from the solar equator to 20 degrees, all these 5 results, more or less, show about 3 layers, 3 multiple flow layers. All of them show multiple flow layers between the solar equator and about 20 degrees latitude. So this is the only consensus we have so far for the Merino circulation. So it's interesting to point out why we have consensus in the low latitudes. I think it's because we observe directly towards the solar equator. If we are able to observe, have another vantage point in a high latitudes, maybe we can have a lot more consensus. So the question is, what prevents us from a better inference of Merino circulation? The first issue I want to point out, just like Aaron also pointed out, is the systematic central limit effect. This is a helioseismic effect that gives us a strong signal in a systematic effect than a real signal. What's shown here is the left panel shows the central limit effect, which is up to 5 seconds in the travel time shifts, acoustic wave travel time shifts. The right-hand side, the right panel shows the Merino circulation induced travel time shift, which is up to 1.5 seconds. So this is really bothering and troublesome. That means the systematic effect is about 3 times stronger than the Merino circulation induced effect. So what can we do? First of all, I think we need to understand what causes this systematic effect. For now, although Aaron pointed out there's some theory to explain the central limit effect, but so far we are not at that point to fully understand it. Secondly, we have developed two different methods to remove this systematic effect. One is to use a proxy. The other one is to set up a linearized equation and solve the equations. These two different approaches give us some results, but it's far from being satisfactory. So this is the first issue. The second issue is foreshortening in the high latitudes. If we observe the sun from the Earth, so 60 degrees is about here. So that means the last 30 degrees is only just a small fraction of what we observe. That means we lose a lot of spatial resolution. A loss of spatial resolution means it will cause the unbalanced power distribution in wave numbers. That means in high latitudes, we can only observe the power in very low wave numbers. But the lower latitudes, we can see very strong power in high wave numbers. The unbalanced power will give us some troubles to understand to do the helioseismology. It may cause some artifacts. The third point is, how does the horizontal component of solar oscillation matter? What we observe from the Earth is just the line of sight signals of solar oscillation. With the increase of latitudes, we have more and more contribution from the horizontal components of oscillation. This may change the phase of oscillation. How does this matter? We don't know. So, from my point of view, observations from a different vantage point, or even better, from above the sun's polar region, will help us solve all these issues and lead us to a better understanding of solar Merino circulation. So let me point out, for HMI and ground-based observations, this is our helioseismic or time-distance helioseismology measurement scheme. So everything, this is about 60 degrees. This is the equator. This is the ray path connecting solar equator and 60 degrees. So basically, in principle, what is inside this red curve, it can be resolved. But look at this. This is just a small fraction of the solar interior. This large part of the solar interior is unresolved. So if we have a high latitude observation, we have a better coverage. We can cover this part. So this can give us a lot more information than what we have so far. Also, this can give us a few advantages. We can avoid foreshortening. This offers us to resolve Merino circulation here. And this also provides us a different vantage point, which can help us to better understand the center limit effect, and eventually lead us to a more accurate, more reliable, more robust inference of Merino circulation. And the third one is if we cross-examine results from the Earth side observation and the pole side observations for the mid-latitudes, for both sides of observations, we are able to derive mid-latitude Merino flows. This is able to validate our analysis method and the systematic effect removal method. Moreover, as my previous speakers have pointed out, if we have two different vantage points, we are able to do a very long ray path study that can give us very deep interior information. For example, we are able to reach the radiation zone and even the solar core. We can understand the structure and the dynamics in these regions. How about observational requirement? Aaron has already pointed out a few points. Here is just some of. I didn't have detailed studies. It's just some numbers based on my experiences. For spatial resolution, we don't need a high spatial resolution to do Merino circulation or rotation. We don't need high resolution. We need a a medium L resolution. That means it's about 200 by 200 full disk. In terms of the duration of observations, I would point out I would like a 6-month continuous coverage. That a 6-month continuous coverage is not from a single vantage point. It's, the spacecraft can move. We can have just one area to be covered by 6 months. That's already good enough for us. Certainly, what I say is not just the low resolution observations. We can also have higher spatial resolution observation in the polar regions. And for that one, we can have, I would hope, a spatial resolution of about 1 arcsecond per pixel with a field of view of 400 by 400 arcseconds. For this higher resolution observation, we don't need a long duration. Possibly, it's just 3 days or 4 days is good enough. In terms of observables, we would hope photospheric Doppler velocity to be done. However, I also like to point out intensity is also acceptable. If we have intensity, we don't have to do very complicated calibration of Doppler, and also we don't have to deal with very high, very large orbital velocity. So intensity certainly has its advantage. But I also want to point out, if we observe intensity, we need to be very careful in selecting the lines, because some intensity lines are not sensitive to solar oscillation, but other lines are more sensitive. So, okay, that's what I want to say.
Thank you, Jean-Wei. We have time for questions, so why don't we go Lisa, and then Paulette, and then Don.
Okay, Junwei, thank you. Very nice very nice talk. I actually have 2 questions for you. The first question is, you showed the differences in the variations, the differences in different observations with people making measurements over different time periods, and you showed that they had very different results. And I wondered if you thought that the multicellular structure of the meridional flow might vary with the solar cycle, and could that partially explain those differences? And then for my second question, you talked about the very long ray paths, which I understand is very important for helioseismology, but I was confused because you mentioned ray paths actually penetrating the radiative zone and possibly the core, and my understanding was that the ray paths would basically be reflected by the tachocline. Do you think you'll actually be able to take measurements as deep as the radiative zone or even the core?
Thank you. For this one, yes, you point out a very important issue. Yes, the Merino circulation changes with solar cycle. We also have some results that's under preparation. Yes, the double cell circulation is strongest during from our results. Is the strongest in the solar minimum, and it gradually evolves into a single cell for the during the solar maximum. This is one important point. The other point is just like what I already said. From the solar equator to about 20 degrees latitude, all of these results using different instruments and for different periods, they all show more or less a double cell circulation. So double cell circulation in the low latitudes, I think, is pretty much established. So this is the first question. Your second question is, I would like to point out the ray path, the low oscillation, the low mode oscillation, like IO is equal to 0, IO is equal to 1, 2, 3. They are able to penetrate through the solar core and to the other side. There's no question of that, no problem of that. Yeah, I mean, some part got reflected, but it's just a small fraction.
Paula?
Right.
6 months is pretty longitude. What temporal coverage? I mean, you're not going to get 6 months continuous.
Right.
So what temporal coverage would you need over that 6 months?
The
80%?
Well, yeah, I would say, 80% is possible, okay. But I also want to point out, it's not a continuous coverage of the whole disk. It's just a continuous coverage of some specific regions.
Don and then Dean.
Going back to your slide with the panels of the different results from MDI and HMI. Panels A, C, and D were all HMI.
Right.
And you accumulate and increase your statistics. So I guess it was related to the first question, but did you do, A is the first 2 years, and then the first 4 years, and the first 7. Did you do years 2 to 4 separately to see if there's a difference in the function of the cycle?
We did. We did a lot of comparisons, but we didn't publish papers on that. So basically, A and C is from different approaches, but from same authors. C uses the same method as A, but from different authors. That's the difference. We are not able to reconcile these results at this point.
Last question or comment from Dean.
So let's see if we can simplify your request. Could you use an irradiance instrument like golf or the Bison instrument and get the deeply penetrating rays as a function of latitude? Because they would give you L, they can get up to, they're still low L, but you can get something. And you could probably get a better data stream on how simple it's going to be.
Well, there are two issues here. One is simple measurements, simple observations. Yeah, it's fine to be simple, but the other issue is low L or high L. To do this research, to do this Merino circulation, I would strongly hope we have medium L up to 300, L up to 300. So lower than that, I'm not sure. I'm not sure whether this kind of research can be done.
So you don't associate going to the core with low L even in the time distance?
We haven't done that, but in principle, we are able to.
Okay, so it's time for the break. Scott, are there any practical issues? Come back at 11? Okay, thank you again to all the speakers of the morning.